In this video, let's see the orthogonal property. If f of z is equal to u plus iv is analytic, then the family of curves u of x comma y is equal to c1 and v of x comma y is equal to c2, where c1 and c2 are constants, intersect each other orthogonally. This is the statement. And now let's see the proof. We know that two curves intersect each other orthogonally if the tangents at the point of intersection are at right angles, or we can say slopes, that is m1 into m2 is equal to minus 1. So if we prove that the product of their slopes is equal to minus 1, then we are done with the proof. So we have the real part u of x comma y is equal to c1 and v of x comma y is equal to c2. So let us take the slope m1 from u and slope m2 from v, and finally let us multiply those two slopes. Okay, so u of x comma y is equal to c1. I am going to differentiate with respect to x, treating y as a function of x. So u, if I differentiate, del u by del x plus del u by del y, because it's a combination of x and y, and then I'm treating y as a function of x, so I'm writing into dy by dx. Right hand side c1 is just a constant, so I'm equating it to 0. From this, what is dy by dx? Push this del u by del x to the other side, you are getting a negative sign, then divided by del u by del y, that is your first slope m1. Similarly, for v also we can write like this. So wherever u is there, change it to v. That's it. So we'll get m2. Now m1 into m2. So I'm multiplying these two. We are getting del u by del x, del v by del x in the numerator, and del u by del y into del v by del y in the denominator. Okay. Now we know that if the function is analytic, it satisfies CR equations. So we are going to substitute CR equations. Either you substitute only for the numerator or substitute only for the denominator, so that it will get cancelled. And if you see this, we have changed only the numerator. So del v by del y into minus del u by del y. So we used CR equations. Ux is equal to vy and uy is equal to minus vx. So all the terms will get cancelled and we will get minus 1. So this is the proof that the curves intersect orthogonally at every point of intersection. And one more thing, the converse is not true. And if you see this example, u is equal to x square by y and v is equal to x square plus y square. So let us check whether m1 into m2 is equal to minus 1 for this. Okay, so I'm going to differentiate the curve 1, x square by y is equal to c1, that is my u, and curve 2, x square plus 2y square is equal to c2. I'm going to differentiate this with respect to x by treating y as a function of x. So this is u by v, write the denominator y first, differentiate the numerator x square, I'll get 2x. Then minus, write the numerator x square, differentiate the denominator y, I get dy by dx, divided by denominator the whole square, just u by v method. Right hand side it's a constant, if I differentiate I'm getting 0. And then denominator, if it goes to the other side, it will become 0. Then push this 2xy to the other side, and then dy by dx is equal to 2xy by y square. 1x will get cancelled, to y by x. This is your first slope m1. Similarly, we are going to differentiate v. Okay, what is v here? X square plus 2y square is equal to c2. So x square differentiation 2x, 2y square differentiation is 4y. I am treating y as a function of x, remember that. So into dy by dx I will get, this is equal to 0. So 4y into dy by dx is minus 2x. Therefore dy by dx is minus x by 2y. This is my second slope m2. And now I am going to multiply my first slope m1 and the second slope m2. So we are getting minus 1. Hence the curves u is equal to c1 and v is equal to c2 intersect each other orthogonally. And also we said that the converse is not true, right? So here we are checking ux and uy, okay, CR equations. So CR equations itself are not satisfied. So u plus iv is not analytic. the idea is, if the function is analytic, the curves intersect orthogonally, but if the curves intersect orthogonally, need not be true that the function may be analytic or may not be analytic. So it is not always true. Similarly, we can prove the result for polar also. So in polar, it is in terms of r and theta, right? So if r is equal to f of theta and tan phi is r into d theta by dr, where phi is nothing but the angle between the radius vector and the tangent. Okay, so angle between the tangent at the point of intersection of curve is phi 1 minus phi 2, and tan phi 1 in tan phi 2 is equal to minus 1. This is what we have to prove for orthogonality. So u, the real part u of r comma theta c1, we are differentiating with respect to theta, treating r as a function of theta. So that is why we have written u r and then r with respect to theta. So we have written d r by d theta, not del r by del theta, same as the previous one. So r as a function of theta alone, plus u theta is equal to 0. So we got dr by d theta. But what is the formula for tan phi? R into d theta by dr. So r into, we are just multiplying r here on the right hand side, that will give you tan phi 1. Similarly, from b of r comma theta, we are getting c2, and we get tan phi 2, because this is some angle phi 1 and this is another angle phi 2. So tan phi 2 is equal to minus r into vr by v theta. So when we multiply these two, tan phi 1 and tan phi 2, and of course we are using CR equations, and hence it is minus 1. So thus the polar curves also, u of r comma theta is equal to c1 and v of r comma theta is equal to c2, intersect each other orthogonally. This is the polar proof. And also I have already discussed about harmonic property, and we proved it in Cartesian, but this is a proof for polar form, same as Cartesian. In case if they ask this question, derive the polar form and show that it satisfies the Laplace equation in polar form, then in that case you can go for a smaller proof in the polar form, CR equation, and then from CR equations you can derive this desired result. So what is a CR equation in polar form? R ur is equal to v theta. We have to differentiate partially with respect to r. Okay, then r into del square u by del r square plus del u by del r into 1 uv is equal to right hand side del square v by del r del theta. Similarly, second polar equation, CR equation, we are differentiating partially with respect to theta, and then we will get this. Okay, so now what you have to do, you've got first equation and you've got second equation. From first equation you've got del square v by del r del theta, and from this second equation del square v by del theta del r is minus 1 by r into del square u by del theta square. One second. Yeah. Now you can see this. So this is what you've got from the second equation. This and this answer from the first equation we are going to equate. The proof is exactly similar to Cartesian. So after equating these two, okay, just divided the entire equation by r, then you will get the desired result. Del square u by del r square plus 1 by r into del u by del r, it's there inside the box, plus 1 by r square into del square u by del theta square is equal to 0. Okay. Similarly, you can prove for v also. So now you have proved that u is harmonic. Similarly, we can prove that v is also harmonic by differentiating partially with respect to theta and with respect to r, and if we equate it, you will get the desired result. So this is the proof for harmonic property in polar, and hence we are done with module 1.